Thank you so much. Yes, thank you. Well, I have to say also thank you to Daniel for doing half of my work for me. So that's quite great. And also thank you to the organizers for giving me the chance to give a talk here. I have to say, as a materials chemist who works in the field of biomaterials and biomedical applications, the conference has been very inspiring for me. I have learned a lot from all of you as experts. So I hope that I can give a little back and motivate you that the AFM or the SPM that you might, or some of you might have in the corner of your labs can actually give you very nice rheological measurements of your biomolecular condensates and conservates. So most of the work has been done during my time at Leiden University, so from Groningen to Leiden, but now I work at Medical University of Vienna, so I'm actually in Vienna. I don't think I have to give an introduction to biomolecular condensates to this audience. I think this is already the third time we're seeing this picture, so I'm just going to skip that. We know that condensates are phase separated, and we know that they are crucial for many of the functions within the cell. But what we also know is that condensates can become solid-like, and their liquid state is actually very crucial for their functionality. And their solidification has been correlated with neurodegenerative diseases. So it's already been 10 years that this paper, as an example, came out that showed that if you have wild-type views in sarcoma, and you look at the phase separation in vitro, after a couple of hours, you see that the droplets stay in their liquid form. But if you have the ALS mutation, like you see here, you see that the condensates start to solidify and they start to grow these amyloid fibrils that we know it's the hallmark of many neurodegenerative diseases, such as ALS, Alzheimer's, and Parkinson's disease. So many people have studied condensate solidification, and since solidification is correlated to a change in mechanical properties, many researchers have studied the mechanical properties of condensates, and this is usually done with bead-based methods. You might know these really fundamental works of Louis Jobert, who developed this methodology of how to measure condensate mechanical properties with optical tweezers, and basically by having beads in the system. So the work is amazing. Optical tweezers are great because they have very high force resolution. The problem with tweezers is that they have a very low force range. And we know that condensates do not stay liquid, they solidify. And it has been shown that the mechanical properties of amyloid fibrils is actually comparable to materials such as collagen and such as silk, which are some of the toughest materials that you have on this planet. So you can imagine that measuring the mechanical properties of the condensate from liquid to solid with the same system, being optical tweezers or bead-based methods, is not really feasible. Not only that, during this conference, we have heard it in talks. I've also talked to people that tell me that they have problems getting the beads into their systems. So it would be very nice to have a methodology that allows us to measure condensate properties from liquid to solid, because obviously the whole field of pharmaceutics wants to develop drugs that studies the solidification and then sees how the drugs counteract it. And then we thought, okay, so let's just look what methodology is used to measure the amyloid fibrils and take it from there and go back and measure the mechanics of liquid condensates with that method. And this is actually scanning probe microscopy, or you might know it as atomic force microscopy. I put this picture here just to remind you that it's the same methodology, just the lateral resolution is a bit different between AFM and SPM. So it's a probe-based method. You have here the cantilever, you have the probe, and you have a laser light focused on the cantilever going to a photodiode. So you can measure the height of the cantilever, and from the deflection of the cantilever, you can measure the force. So we said, okay, let's start to develop or investigate how we can measure the mechanical properties of condensates using the scanning probe microscope. And why SPM? Because in comparison to optical tweezers, not only it has a larger force range, the force range is also on the higher side of the spectrum, which is quite nice. So theoretically, it should be possible to measure condensate mechanics from liquid-like to solid-like. And this is what we did. We used poly-L-lysine and heparin condensates. So I have to go back to the talk, the great talk of Matthias Balloff that was telling us about the interactions of glucosamine glucans with positive counterparts. But the reason we chose poly-L-lysine and heparin was actually a bit different. We chose it because the reagents, you can buy them. They are commercially available. They're not even that expensive. When you mix the system in a buffer with some crowding agent, you actually get quite stable condensates. So for developing a new methodology, it's a very nice and stable system. So we took poly-L-lysine and heparin condensates, and obviously, we wanted to do everything you can do with optical tweezers. So really be able to measure the storage modulus and loss modulus, which we have learned already today what they are, and how to measure them with rheology. And that's why we did rheological measurements on our condensates with scanning probe microscope. So here you see the poly-L-lysine and heparin condensates just on the bottom of the dish. This is the cantilever, so you see it from the top. And then you see in this video that the cantilever indents the condensate. But what you don't see is that afterwards, it modulates the condensate at a very, very small height. So it's only 40 nanometers. You don't see it in this video. You just see the indentation. And then we have modulation at various frequencies because we are doing rheology. So even though you don't see the modulation in the video, you see it from these graphs. You see that the height of the cantilever, you see that it approaches to the condensate. We have pause to make sure that the system stays stable. Then we have modulation of the height at various frequencies. And then we again detach from the cantilever. And you see the response of the system very nicely from the force. You see that in the beginning, there's no contact between the cantilever and the condensate. We have an abrupt contact followed by the indentation, pause for the system to reach stability, and then response of the system at various frequencies, which, as we expected, is much higher at higher frequencies, which you also see very nicely from these two graphs. So here you see the height modulation is the same, but the response is higher at 100 Hertz frequency in comparison to 1 Hertz. So we have height, we have force. What can we do from that data that we get from the machine? Obviously, we can make spring constants. We can calculate spring constants. And for that, we collaborated with Oskar Armbruster, who actually works at Boku University here in Vienna. And they did some of the calculations for us. So we got the spring constant, and we called that actually the experimental spring constant. And we very quickly figured out that in order to get to the elastic and viscous moduli from our spring constant, there are quite a couple of things that we need to take into consideration. So the first thing, so maybe we saw it in the last talk, you see the complex spring constant, you see the real part being the elastic, you see the imaginary part being the viscous, and you see the phase. So the first thing we had to take care of was the phase lag of the cantilever, because it's obviously moving in a crowded environment. So it has a phase lag. We removed that, and we get to what we call the system spring constant. You see it schematically here, that it still has the contribution of the cantilever spring constant in it. Then we had to remove that one. What we call here is the particle spring constant. And that one still has the contribution of the spring constant of the surface energy in it. And that was the easy part, because actually Luis Chavez showed that at lower frequencies would be the frequency being 0, but we don't have that. So we take the lowest frequency, and at lowest frequency, the contribution of the bulk material is negligible. So it means the spring constant you have is actually only the spring constant of the surface energy. So we subtracted that, which is we subtracted that from the whole system, and then what we get is the really bulk material spring constant. So this last step is just using a Hertzian contact model, which describes the contact mechanics between two curved surfaces on each other. And by using the Hertzian contact model, we get to what we saw in the last talk. We get to G prime and G double prime. So the elastic and the viscous moduli. So this was great, because this is what we also get with optical tweezers. We were really happy. And obviously what you can also do is to fit the G double prime and get to the viscosity of the sample. So very happy that we got everything that one can do with optical tweezers, but obviously this is a new method and one has to at least validate it somehow. And we took FRAP just because of accessibility. So we made fluorescent condensates. We made 5% fluorescent poly-L-lysine. And then you have the recovery of the system, and we saw actually the equations of that yesterday in another talk. From the fitting of the recovery, you can get to diffusion constant, and from that you can get to viscosity. So we set up to compare FRAP with scanning probe microscope, and we have heard in this conference quite often that, condensates are sensitive to salt, and their material properties really depends on salinity, and we took advantage of that. We made condensates at various salt concentrations and first measured them with scanning probe microscope and calculated the viscosity from that. And then we repeated the experiments with FRAP. So here you see exemplary micrographs of the recovery, and here you see the recovery data. So it's quite well known that diffusion is faster at higher salt concentrations, and this is also what we see here. And by fitting those, we got the viscosity, and we compared them to the viscosities we got from SPM. It was very nice to see that they are in quite good agreement. So this was the moment that I got very happy. I was like, yay, what I'm measuring actually makes sense. This is not complete nonsense. So the method was validated, but obviously the whole reason or the whole motivation to use scanning probe microscope was to show that you can measure rheological properties, like I said, from liquid-like to solid-like. And in order to show that, we again took advantage of the sensitivity of the system to salinity. So again, made condensates at 1 molar KCl, but this time I did the experiments a bit different. So I let the condensates settle, I measured them, and then I carefully removed the supernatant and changed it with lower concentration salt. So everything else stays the same, just the salt is lower. And you see that morphologically, the condensates start to become more gel-like, and rheologically, they become to this very variable, weird intermediate state. And then afterwards, I again went down with the salinity, with the salt concentration, and you see that they become from this squishy liquid condensates to this crispy gel-like, and also the rheological properties becomes G prime becomes larger than G double prime, which we heard in the last talk is an indication of the gelation. So this was very nice because we measured with the same system from liquid-like condensates to solid-like or gel condensates. And since the rest of the presentation is white, you can probably imagine what I did next. I again changed the supernatant with salt concentrations that were higher, and you see that we started to rejuvenate the condensates. They morphologically and rheologically start to become again more liquid-like. And if you go back to 1 molar again, obviously you have condensates that are liquid, look similar to when they did before, and also looking at the rheological properties, G double prime again, so the viscous modulus becomes again larger than the elastic modulus, and the response of the system becomes frequency dependent, so it means they rejuvenated. So this was quite nice because we showed that we can measure from liquid to solid and back to liquid, which again, for medical applications and pharmaceutical applications, it would be great to have the same system and see the solidification of the condensates, and then use your drugs to be able to see the rejuvenation as well. So this was quite successful, but then again, I'm in the applied field. I work in biomedical applications. So I would like to see also how condensates interact with cells, and why is this important? Again, I have to go back to Matthias Balof's talk about the interactions of heparin sulfate in the extracellular matrix. And there's this very nice paper that actually shows heparin sulfate on the cell surface interacts with growth factors in a condensate-mediated way. And they did actually quite great job to show that they're really liquid-like. And if you remove the heparin sulfate from the cell surface, then you don't have condensates. So this is a great paper. And then I thought, okay, it would be nice to also measure the mechanical properties of condensates while they're in contact with cells with scanning probe microscope, obviously. But in order to do that, this becomes a little more cell culture and a little less biophysics. I apologize for that. In order to do that, I needed to have a system that supports the viability of my cells. And this system obviously has a culture medium, and then it has nutritions for the cells. It also has like serum, so everything the cells need to stay viable within a medium. And I made this culture medium, basically. So you buy the culture medium, you add the augmentation to it. And what I did next was to just add the poly-L-lysine and heparin sulfate in it. And three very nice things happened. First of all, I had condensate in my culture medium, which was on its own quite nice. Secondly, I needed no crowding agent because the system is full of proteins. So it would basically be if you're using BSA as a crowding agent. So I needed no crowding agents. And the third thing that was quite nice was that I also needed no surface passivation. So again, all the proteins that were in the culture medium worked as a surface passivation, and I didn't need to passivate my surface, which all of them means that I can also culture cells in this medium, which was quite nice. So we see here the condensates. We obviously also characterize them with our scanning probe microscope and with FRAP, and we saw that they are liquid also in the culture medium. And the next thing was take some cells. Here I just took some fibroblasts. It's a cell line. And removed the medium and added a medium that had the condensates in it. So I had the poly-L-lysine and heparin sulfate in it. Put them back in the incubator for 2 hours. So at 5% CO2, 37 degrees. And after 2 hours, you see that the condensates are settling also on the cells and that the cells stay viable. I have to say they are not very happy, but they are at least viable. And then I wanted to again measure the mechanical properties of the condensates on the cell. And this was the moment that we started thinking, okay, when we are using the Hertzian contact models, like we did for the experiments I already showed you, it actually assumes that the G of your probe and the G of your surface is infinitely times harder than the material you're measuring, which in this case is not true. It doesn't hold because cells are also quite soft, and while you're indenting a condensate on the cell, you cannot assume that you have zero indentation of the cells like you would on a plastic dish, which means we had here 2 variables that we didn't know. So we didn't know the G of the condensate, and we also didn't know the G of the cells, but this was actually no drama because you can measure the rheological properties of the cell beforehand. And this is what we did. We first probed the cells, we did rheology, and then we introduced this, what we call a stacked Hertzian model. So it actually takes care or takes into consideration the indentation of the surface at each frequency. And by that, also at each frequency, you can get the mechanical or the rheological properties of the condensate that is sitting on the cell. And we did that, and then afterwards, we again probed the condensates while they were sitting on the cells, like you see here. And we got the rheological properties of the condensates also while being in interactions with the cells, which again, for me, as someone who works in the applied field, is quite cool. So what can I say at the end? What can we conclude? So I could show you that with scanning probe microscope, we could measure rheological properties of single microdroplets from liquid to solid and back to liquid when they again rejuvenate, and this is quite nice. And that this is the direction I'm working on right now. So it's still this condensates on cells and the extracellular matrix is still quite new, and this is what I'm working on. But I would really like to understand. So use this studying the mechanics to understand the condensate membrane interactions, because we know how membrane wetting is crucial also in many biological fields. But like any new methodology, it also has limitations, which I would like to also give you, so you know that if you want to use it, you have to really think about your application. So one of the limitations is that the droplets need to be settled on a surface. So it's not like with optical tweezers that you can trap them. They are in the liquid, they are in the nice round form, and you can just trap them and start modulating them. They need to be settled on a surface, because obviously I cannot probe something that is swimming and then I will just push it down. So this is a limitation. The second limitation is that the Hertzian contact model assumes that the droplet is homogeneous, So we've heard also that, you have core shell droplets. Also during aging, this is very important because like for FUS, it has been shown that the gelation starts from the boundary and then travels inwards. So this is another limitation because Hertzian contact model does assume the condensate to be, or the droplet to be homogeneous. But this is also something we have started looking into actually for like core shell models and how we can introduce our new system to measure that. And the third limitation is like atomic force microscope. Scanning probe microscope is restricted to surface measurements. So if you, for example, have a core shell, you can't just press past the shell, go into the core, and then modulate just the core. Obviously, you can measure the whole system, and you would be able to subtract it, but it's not like a beat system that you can, put in exactly where you want to measure and then modulate. It does have limitations as well. So with that, I just want to thank my old group in Leiden, the medical systems, biophysics, and bioengineering. And also, I would like to thank Liru Feng, which is a member of the Louis Jobert group, who is also now at Leiden University. And if you're interested, we can talk about how to use AFM for rheological properties. The code is also available, so just write me and I can give it to you. And I'm very excited to answer any questions. Thank you.